thank you so much for joining me. In today's video segment, we are going to apply Coulomb's law to ionic bonding. Now, when I'm talking about Coulomb's law and applying it as what I call a first level understanding of bonding or atomic structure or the context, it gives us an initial qualitative understanding of the structure and hence the function of the substances we're dealing with. In this case, we're going to talk about it in the context of ionic bonding. Now, I'm not going to be using Coulomb's law as a force, which is proportional to the radius squared. Instead, I like to talk about Coulomb's law as potential energy. Now, potential energy is given a number of symbols. I'm going to call it EP for potential energy. I think that's hopefully one of the clearest. And that's going to be a constant. And in our case, we're talking about the charge of our cation times the charge on our anion divided by the distance between them. Now, this is very, very important that you get this part straight. I graded the AP test recently, and one of the main difficulties students had is they couldn't define that distance. If you're going to apply Coulomb's law, one of the first things you want to do is, or really any mathematical formula, make sure you define your variables. So our distance would be the radius of our cation plus the radius of our anion. Okay, so as our cation and anion get closer and closer and closer and closer together, I want you to notice that the potential energy becomes negative. That's because a positive times a negative is going to give us a negative potential energy. So negative potential energy is going to be more attraction. It's going to tell us that we're talking about a system that is typically more stable. And it's a system that takes energy to break the attraction. That's a common misconception that we have in chemistry that we have to kind of put an end to. I think it starts with the way breaking of ATP in biology is discussed. But what we're talking about here is attractive forces, and in biology as well, they're talking about coupled reactions that release energy. If it's an attractive force, any bond takes energy to break. So the phrase I like that I've been using in the last few years is takes to break, freeze to form, takes to break, freeze to form. Okay, so this makes it more stable. Okay, now it will, as we continue to decrease, what we're going to do is hit what I like to call a sweet spot of stability. That's our bond length. And it's an average bond length because atoms vibrate. Unless we're at 0 Kelvin in a perfect crystal, atoms are going to have some motion and they vibrate along that average bond length. So that's kind of our sweet spot, and we report our average bond lengths. So if we were down here and we wanted to break that bond, we would have to get up to a distance equal to 0, and that would represent the energy that it takes to break that bond. Okay. Now, let's look at this qualitatively for just a minute, and that's all we'll use it for typically in first year chemistry. As you increase the magnitude of your charges, you will make, and I want you to be careful how you phrase this, your potential energy will become more negative. You could talk about it as lower because it is lower on the y-axis, but I would really avoid words like bigger and smaller. You can talk about absolute value as a magnitude, but man, make sure your language is really, really clear on that. Now, if we, in this case, increase the distance between them, we're going to make the potential energy less negative, or you could say higher, right? As distance increases, they become less and less and less attracted to one another. Now, if you're comparing say two ionic compounds and you want to look at their properties, remember structure determines function. If you're comparing and you want to compare their properties, the phrase I like to say is charge trumps radius. If you have a situation where one substance kind of wins the strength of the bond based on charge, and the other wins the discussion based on the radius of a cation or anion, and hence the distance, typically, I would personally predict the charge would win, absent of any evidence, some data to tell me otherwise. So if I was forced to make a choice, I would say charge trumps radius. Now, a couple things I want to mention about this before we're done is with ionic compounds, we will often relate this to the lattice energy. We use the word lattice because ionic compounds are alternating positive and negative charges in a lattice and so forth. And that lattice energy is defined in terms of, I'm going to use sodium chloride as an example, are gaseous ions forming the solid, I don't know why I switched to lithium there, my hand's not keeping up with my brain today, the solid sodium chloride in this case. So it's gaseous ions going to the solid salt. And in this case, this would be the energy that was freed to form. So it would be negative. It would be the energy going down. Okay? And the last thing I really want to mention here is I wanted to show you what this looks like if we're talking about repulsive forces. If you try to, pull out or stretch into a thin wire or even any type of shearing motion on your ionic compound, what happens is if one layer gets pushed one way, if the other layer gets pushed the other way, we get positives by positives and negatives by negatives. Well, now what we're talking about is repulsion. So repulsive forces increase this way, but repulsive forces are positive potential energy. So this would look something what it looks like if we're talking about our repulsive forces for ionic. So I hope this helps you out a little bit and helps you understand Coulomb's law, because I am finding as I teach more and more that it is a very powerful way to help us understand how structure does determine function and how we can predict. Thanks for joining me.